Petri nets. Petri nets are named after Carl Petri, who created them in the 1960s to model resource contention. Consider the case where you've got certain resources that are sought after by different processes. 2 or 3 people, for instance, try and access the kitchen sink at the same time. The kitchen sink is the resource, and the people are the tasks, jobs, or processes, abstractly, that are trying to access the resource. So it's a shared item. The problem is that the people, who are modeled in computer science generally as agents, processes, jobs, or tasks, all need the same shared resource, the sink, at the same time. Since only one person may access the sink at any one time, there's contention for this resource. Modeling this sort of dynamics is what Petri nets are very good at. Petri nets are a kind of hybrid modeling structure containing the concept of state and event in a way that both are given equal footing and power, to the extent that both have specific components which embody these functions. Let's go ahead and define the Petri net formalism. A Petri net is a combined state-event model with the state space being represented by places and events by transitions. If we look at the Petri net formalism itself, the Petri net is equal to a tuple with 4 items within it, 4 components, if you like. P for places, T for transitions, and both P and T are sets. I, which is a function, not a set, and stands for input, and then O for output. So P and T are both sets, and then I and O are maps or functions that map either places to transitions, which is what happens with input, or transitions to places, which is what happens with output. Let's go ahead and draw some simple Petri nets. First of all, a place is often represented as a circle. So that's a kind of a default 2D diagrammatic icon for representing a place. So we'll go ahead and put place like that. Now, transitions are often in the same diagrammatic fashion represented as a straight line, or perhaps a bar like that. And then what happens then is that Petri nets are composed of places connecting to transitions. And so the connector or trace is often represented as an arrow, like this, and an arrow going out to another place. So formally, a Petri net is called a bipartite graph because it's a directed graph that's composed of 2 types of elements, namely places and transitions. So we'll say this is place number 2 and this is place number 1. Now, in addition to places and transitions, we need some sort of control or flow mechanism, and we achieve this by creating something we'll call a token. And so we'll fill a little circle in here and say that this thing right here, and I'm just drawing the arrow for emphasis, is going to be a token. Alright, so what happens then is that in the execution of this particular Petri net, and this is a valid Petri net, it's got a couple of places and a transition, this token moves through the transitions to the outgoing places. So if we want to kind of hand animate this, what we do is we'll go ahead and say, all right, at time 0, this is what happens. well, at time 0 there would be a token here, but at time, say, 1, if this transition over here is going to take 1, that the token moves from left to right, and so it moves over to here. Now there's no reason why we couldn't have yet another transition right here, and yet another place. And so at time 2, the token would move from here over here. Now let's go ahead and look at some other aspects of Petri nets. Just from this example right here, you get the feeling for what might happen in a simple kind of Petri net. But certainly, and we'll just use bars for transitions this time, not only can I do this, but I can also, for instance, draw another place and put it up like that. And of course I can do the same thing with the output. I can have more than one output. And with this example, we can show the rule for Petri net execution. What happens is as follows. Petri net execution or hand simulation is performed by looking through every transition, every transitional element within the Petri net. In this case there's only one, this one right here. And for each transitional element, you look through every input place. And for every input place, you say, is there at least one token in that place? If that's the case, then this transition is said to fire, or to be capable of firing. And the concept of fire is a bit like a neuron, metaphorically. So if we have at least one token in here, and there's no reason why we could have more tokens, I may put 2 in here just for the display purposes, then this transition right here can fire. And what happens when you do fire is that one token is removed from every input place and one token is produced in every output place. So I'm going to go ahead and get rid of one token. In this particular example, it doesn't matter which one, and I'm going to go ahead and produce one token in every output place. So that's the hand simulation of that particular Petri net. At the next time, these tokens aren't going anywhere because there's basically nowhere for them to go. There are no outgoing arcs here leading to other transitions that might process these tokens. Furthermore, if we look over here, there's a token in this input place, but there's no token here, and therefore this transition can't fire. It needs at least one token in every input place to fire. So a token being here as it is not sufficient for this transition to fire because there's nothing in here. Now let's take a look at another example, and what we're going to do is we're going to employ a little bit of feedback in this example. We're going to put something like that, and we're going to create an output like this, except now we're going to have some fun and do a feedback like that. Now let's see the behavior of this. If we put a token in here, this transition can fire because it only contains one input place, and that input place does contain a token. So what happens then is we get rid of that. A token gets produced over here, but a token also gets produced back in here because not only is this an input place to this, it's also an output place to the same transition. So we put a token back in here. And so this is what the Petri net looks like, or the animation of the Petri net looks like at the next time. Now, as one can imagine, as you keep on going forward in time, For instance, we go over and produce yet another token over here, and of course another token back here, that this Petri net is a kind of digital counter, because it counts the number of times that the Petri net is simulated and keeps the tokens in the repository being this second place right here. Now, there are other cases. There's all kinds of varieties of Petri nets, and we won't really go over this except to specify one example of it. But you can do things like this. You can have multiple arcs from a place to a transition. You could do something like this. And all this means essentially is that you need one token per trace or per arrow in order to make this fire. And so the firing would take two tokens, one for each of these arrows. It would erase those tokens, and it would produce a single token over here. Note there is no conservation of tokens in Petri nets. You have to execute the Petri net by following the simple rule of taking the one token from every input place, firing the transition, and producing a new token in every output place. We've seen the basics of Petri nets in terms of places and transitions, but there are many different types of Petri nets. The standard one is the one that we have discussed. We've got the concept of tokens flowing through places or landing in places but flowing through transitions. So the places can be considered temporary repositories for the tokens, which flow through the transitions, which kind of are machinery or process the individual tokens. We also can have colored tokens, and by colored tokens it really means that the tokens can have integers or different values assigned to them. In other words, they can have different sorts of names or integers, or they can be real valued, or they can have tuples assigned to them. They can have extra data or information attached to them other than just simply being black tokens. We can also have time transitions, and by having time transitions we allow the Petri net transitions to each occur at different rates. It may take certain transitions a smaller or less amount of time to operate than other transitions. So colored token logic is different than the the standard transition logic, which is if there's at least one token in every input place, then place tokens in output places. This is the standard logic for Petri nets. Whereas the colored token logic would be keep the above, meaning keep the standard transition logic, but add if the color of the token equals whatever the integer or complex value is or piece of information, then perform some specific operation. And in this way the transitions themselves become more than mere simple token processing filters, but they also become general purpose repositories for pieces of code and functions. Timed Petri nets, we can have continuous time versus discrete time, and now we'll go over an example to demonstrate timed Petri nets by also including the concept of input. Okay, let's go ahead and take this example as a way to talk about 4 different concepts within Petri nets. We're going to talk about the idea of state, because so far we haven't really talked about the state of a Petri net, color, input, and the concept of time, because we're going to allow this to be a timed Petri net. So the Petri net in question is going to be this very simple looking structure right here. It's got 2 places and a single transition. All right, let's go ahead first of all and talk about what does it mean to have a state of the Petri net. The state of a Petri net is going to be a tuple that represents the number of tokens in every place within the Petri net itself. So for example, let's say that I've got a Petri net at some particular time, and at that time the Petri net looks like this. I've got a token in this place and no token over here. Furthermore, let's just call this P1, P2, and since there's only one transition, I'll just call this T. The state of this Petri net at any particular point in time is going to be the number of tokens in P1 and the number of tokens in P2. I'll put a little pound sign to designate number of. So the state here would be 1, 0. Once this Petri net has executed, we know from our prior example that the token moves over from there over to here, which means that the state moves from 1, 0 to 0, 1. Petri nets are not finite state, as in finite state machine or automata. They're infinite state machines. So there can certainly be an infinite number, need not be a finite number of states for this kind of machine or network. Now we can see that if the Petri net had 10 places, then I'd have a 10-place tuple here, and the state space would be 10-dimensional. And so that gives you a concept of how state is defined within Petri net. Now let's look at the concept of color for this Petri net. What we've done is we've made it so that this particular Petri net can have one of 2 colors. It can have red or blue. So what I'm going to do is I'm going to take out the black token, which is the only color available until now. I'm going to make it so that we can start out with a red token over here if we want. Or if we like, we can have a blue token. And we can certainly have a red and a blue token within P1. That's not a problem. So this is a little bit more than we could do before. Again, the concept of color is just a nice visual mechanism and a metaphor for talking about structured data or information attached to each token. It basically says that you can have some arbitrary information attached to this token, identified visually as blue, and then some other piece of information for this token visually identified in this example as red. So far we've talked about the concept of state, and we've introduced the concept of color literally by taking blue and red. Now let's go ahead and look at the concept of input. So far we haven't talked about input. With finite state machines, we know that input came from outside the machine and was processed on the arcs that were found between states of the finite state machine. And if the input equaled or was less than or some other relation in comparison with say another value, then you could move from one state to another. What we're going to do in input here is we're going to say here's time, and this is u, which represents the input, and that we're going to say our input over time is going to be, of course, then u of t, which is defined graphically by this figure right here. U of 0 is going to be equal to 1. We're going to let 1 be red and 0 be blue. And you're going to have a kind of a stepwise function that if we connected the dots, you get something like this. Now the question is, all right, this gives us colored tokens, it gives us an input signal. How on earth do we get an input signal into this Petri net? Well, what we need to be able to do is we need to be able to take the input and attach it to the Petri net somehow. The input needs to flow into the Petri net in some fashion. One way of doing this, kind of the simplest way, is to just say, take a place in the Petri net, say P1, and let all the tokens from U of t just flow into that place over time as specified in this graph. So then what we would have is at time 0, we would have this Petri net right here. Because at time 0, we can see that at time 0 we have a token that's deposited into P1, and that's the situation we have. Now, we haven't talked about time yet, and this is where we're going to talk about time. We're going to say that this transition takes a time delta of 3. So we'll say delta t equals 3 for this transition. That is, it takes 3 time units for this to operate. That is, once tokens are marked, we'll get to that in a moment, for being absorbed by this transition, they won't be deposited into the output places until whatever that time is plus 3 time units. Now, I said I'd get to the concept of mark. When a transition marks a token, it means that that transition owns that token, that the token will flow through that transition, not necessarily immediately, because this is a timed Petri net, but at some time in the near future, that token will go through that transition. This is a form of reservation. In effect, the transition has reserved that token for part of its execution. So this comes into play right here, is that we designate the concept of a reserved token by just putting a little circle around it. So at time 1, what we've got is we've got the token that we get from input. This guy right here is this token, and then this is just a little circle around it, showing that this is marked for execution by this transition. Now this may seem silly right now, but in another kind of Petri net, you might have other transitions. For instance, you could have a Petri net like this, and in such a case, it wouldn't be clear without the concept of reserved token of which transition would get to fire the token, this one here or this one here. This is a non-deterministic situation, and what happens is that there needs to be some kind of conflict resolution or some resolution of sorts to figure out which transition gets the token, this one or this one, when you have a Petri net with outgoing arcs from the same place but to different transitions. Okay, anyway, getting back, so far what we've done is we've processed these two. At time 2, yet another token appears right here, and we're going to show this as being reserved. And so we have a situation where we have 3 tokens in here, which makes sense. 3 tokens in the input stream. At time 3, something interesting happens. At time 3, we end up putting a blue token in here. Okay. But the token that came in at time 0 has now gone over to P2. And of course, got the wrong color there, so let me go ahead and erase that. So this token right here is, at time 3, is this token here. It has taken 3 time units because of our delta t equaling 3 for it to get from here over to here. Meanwhile, we have these, and at the next time unit you can imagine that one of these will end up over here, namely this one right here that came in at time 1 in the input stream will end up over here, because at time 4 this is what happens. We add, at time 3, we add delta t equals 3 to 1, and that means at time 4 this one goes through the transition and ends up over in P2. So all this is the delaying mechanism. It just means that tokens that appear over here affect their way through this transition over to here, but time 3 time units later than when they were deposited over in P1. As examples of Petri nets, we'll look at a manufacturing line, which represents a pipeline where raw stock is piped through on the left, through lathe and a drill, and then finally put onto an automated guided vehicle which drops the finished part into storage. And we'll look at the dining philosopher's problem, which from our perspective we're not considering so much a problem as an example scenario that can be modeled. We're going to go over an example which represents a manufacturing line with 2 robots and 2 machines. So what we'll do is we'll draw up this example as follows. We'll say that we have some raw stock in the form of cylinders, metal cylinders. And this raw stock makes its way into the first workstation cell of the manufacturing floor. And in this cell it's going to encounter an accumulator, A robot arm, and this is seen from the top, we'll call that R, and then a lathe, which will represent as L. Then from the lathe we will go into a drill press, and we'll use the same things: accumulator, robot arm, and D for drill press. And then we'll have a kind of an elliptical track that an automated guided vehicle runs around, automated guided vehicle AGV runs around, taking the finished parts and putting them in storage. So we'll put a storage over here. So let's go through this from left to right now that we've got the diagram up. We have raw stock, which can be considered to be a metal cylinder, a solid metal cylinder. A lathe will turn this and create a kind of a barbell shape. Like that. What happens is that the raw stock gets put in an accumulator. An accumulator is just what it sounds like. It's a place where these accumulate. You find these kinds of things in drugstores and pharmacies, candy stores, places where, just about any store really, places where you have an object which needs to be dispensed, and needs to be dispensed efficiently. So often you have either some sort of linear stack of the thing that needs to be dispensed, with the dispenser being at the bottom. Or you can also have things in a kind of a spiral form, that they start at the top and they just using gravity come out the bottom like this. So this is what we mean by an accumulator. An accumulator takes something from the top, stores it for use by whatever machinery is waiting for it. Now in the case, of course, of a drugstore or candy store, it's the person that buys the candy out of this dispenser. But in the case of manufacturing floor, it's going to be some sort of machinery or person that handles the part. Okay, so this raw stock goes into the accumulator. The robot arm takes it from the accumulator and gives it to the lathe. So the robot arm is a kind of a swivel mechanism like this, which goes to the accumulator and then feeds the lathe. The lathe does this, creates a barbell shape, and then feeds it to the drill press. And the drill press basically just takes a drill and drills it down the center of this in order to get a barbell, but now with a drilled hole down the middle. And so this is the finished part. It's been lathed, it's been drilled, and now the automated guided vehicle runs around the track, picks it up here, and puts it into storage. So this is an example manufacturing floor that needs to be modeled somehow. And we're going to use Petri nets in order to model it. But just getting back to this second section, this is exactly the same as the lathe based workstation, that you've got an accumulator, robot arm, and a drill press. So let's go ahead now and draw the Petri net right above the schematic for the manufacturing floor. What we'll do is we'll say that the raw stock is represented by tokens, and we'll put a place right here. And raw stock, of course, could be dumped in by an input to this system from outside. We'll say that robot number 1, which is this one right here, R1, is defined as this transition. And we're going to put a place here. We're going to give this to the lathe, L. And then, of course, there's going to be some sort of transit or transition mechanism, perhaps a belt, that takes the part that's been lathed and moves it from here over to here. And so we'll just label this transit over to the drill press. Now we're not finished yet. We're going to take an arc from L and move it back to R like this. So this is a kind of a synchronization token. Whereas this black token right here represents synchronization, this actually represents the raw stock. So what happens is this: R1 says, oh, okay, I can go ahead and execute because I've got at least one token in every input place. I got a token here, which represents the raw stock. And essentially this means that the lathe is ready. And when it's ready, these two tokens disappear from their places and a new token appears here. So let's go ahead and just do that. We'll erase this token and erase this token. Okay, now what happens is at the same time another part, raw stock, could appear here, but until the lathe has actually finished operating, the robot arm will be unable to provide the lathe with the next piece of raw stock. So this is what this synchronization token actually provides. It says, hey, the lathe has to complete its thing before, of course, the token can appear here and here. I'm going to go ahead and erase this one. And at that point, then this thing can fire. So this provides a useful mechanism. The Petri net provides a useful mechanism for specifying the resource contention and for saying that the robot arm has to wait to deliver pieces and parts from the accumulator over to the lathe. So this Petri net right here this entire operation right here maps to this, where you have the raw stock, and this piece of the schematic right here. That's what we're modeling. So this is modeling this. Now this Petri net, the Petri net for this is going to be identical to this, and then for the automated guided vehicle, the piece of the Petri net that would represent this part of the schematic where the AGV runs around can be represented in many different ways. It could be represented, for instance, by having a place here, a transition here, and then some way of obtaining a cycle like this. This S would be for storage, and then we would have a situation where you'd have a bin that would be located right here, that would be a bin that would be contain parts taken by the AGV. So the AGV's operation would appear as follows. It would go through here, the token would pass through here, be put in storage, and then the AGV's operation is captured to some extent by this cycle. The dining philosopher's problem in operating systems is represented as follows. You've got a table, and there are 5 philosophers, and so we're looking at an overhead view here, the heads of the philosophers. And each philosopher has 2 chopsticks. I'm going to draw the chopsticks just as simple lines. So the situation that is that for a philosopher to eat, that philosopher needs access to both the left and right chopstick. So if this philosopher right here is to eat, he needs this chopstick and this chopstick. And so the resource that is the source of contention are the chopsticks, because if this philosopher eats, what it means is that this philosopher can't eat, because this philosopher also needs this one and this one, and so this one is being shared by both this philosopher and this philosopher. And so if this guy eats, this guy and this guy right here cannot eat, because this philosopher is taking one of their chopsticks, the left chopstick for this one and the right chopstick for this philosopher. However, if this person is eating, then there's no reason, for instance, why this person can't eat, and either this one or this one, but not both. And so 2 philosophers can be eating at any one particular time. And the order in which they eat and who gets the chopstick next is the subject of a lot of material in operating systems and the concept of fairness in resource allocation. But from our perspective, we just want a way to model this process. So we're not particularly trying to optimize anything or introduce fairness, we're just trying to model it. And the Petri net turns out to be a good way of doing this. So what we do is to model it, and we're going to go ahead and we'll model this philosopher right here, is we say we put 3 places in like this, and we put a chopstick here and a chopstick here. So this is this chopstick and this chopstick right here and right here. And then we put a transition here, and we put 3 arrows into this transition. We say that a philosopher is eating, and if they're not eating, they're resting. I'll put another arrow here, a transition, and then we put an arc there back to here, and then we put an arc there and an arc here. So this is a kind of a synchronization token, whereas these 2 tokens are specifically represent the chopsticks. Now, what will happen then is this is one philosopher. If we want another philosopher, then we draw another piece of the puzzle right here, and we draw exactly this same schematic, or this piece of Petri net over here. So I'm not going to draw the whole thing. I'll just go ahead and draw the part that's interesting. I'll just go ahead and bold these lines representing the individual transitions. All right, so what happens then is if this philosopher right here, we'll call him P1. This is P1. If P1 decides to eat, then by nature of the Petri net, these three tokens would be absorbed by this transition, and then at some point this transition will fire depending on the delta t for the transition, if it's a timed Petri net, and a token will appear here. And then this, of course, can fire, and when this fires, there are three outgoing arcs producing tokens in these three places. So when the tokens are absorbed, getting back to this firing of this transition, clearly when this token is absorbed by this one, then this transition can't fire. And so this captures the exact notion of the problem that we were originally talking about, in that when the rightmost chopstick of P1 is taken, namely this one right here, this chopstick, then this philosopher can't eat because the philosopher must have two chopsticks. And that makes sense because if you get rid of this token right here, then this transition can't fire. And so without actually drawing the entire Petri net, you get a good feeling or concept, idea of how we would take this one piece right here, replicate it 4 more times around the table, and by doing so, generate the entire Petri net.